Okay, we are trying to do the waves structured worksheet. I'm going to discuss the first question. If you haven't done it, or if you haven't at least read the question, please pause the video and go and read the question. Okay, so the first question, a long rope is held under tension between 2 points A and B. Point A is made to vibrate vertically and a wave is sent down the rope towards B as shown in figure 5.1. Okay, the time for one oscillation of point A on the rope is 0.2 seconds. The point A moves a distance of 80 millimeter during one oscillation. The point A moves a distance of 80 millimeter during one oscillation. Point A, the time for one oscillation of point A on the rope is 0.2 seconds, and the point A moves a distance of 80 millimeter during that time. Okay, so explain the term displacement for the wave on the rope. So we discussed about the definitions of different terms in the context of waves. So if you could go back to that notes. So the definition of displacement, these slides are there in files, I think. The displacement of a particle on a wave is its distance in a specified direction from its rest position. So when you are defining displacement, okay, so when you are defining something like displacement in the context of a wave, now one of the common mistakes the students do is they try to define displacement generally, that is like the shortest distance between 2 points in a specified direction. That is the definition of displacement as a vector in a general term, in a kinematic situation. But when you're defining displacement in the context of a wave, there are three things. One, it is the displacement of, it is that of a particle, you have to define that. So in this case, it is that particles on the ropes which are going up, down, down, up. So it is that of a particle, and it is the displacement of a particle in displacement is the distance moved by a particle. So it is that of a particle, then it is the distance moved, okay, and then specified direction. So you have to define whether it is the direction in terms of like above or below or right or left. The fourth important one is the equilibrium position. So there are four aspects to the definition. The displacement is there, then it is about that of a particle, displacement of a particle, displacement is the distance moved by a particle in a specified direction from the equilibrium position. So there are four aspects to it. So that's what's expected in this question. So if you look the mark scheme again, displacement is the distance the rope or particles are above or from the equilibrium mean rest position. So here they are not talking about in a specified direction, but it's better you mention about that as well. Okay. Then here it is not asked, but if let's say that they are asking you to define the term amplitude. Now they are talking about displacement. If they ask you to define amplitude, now the definition of amplitude, if you see, is given as the amplitude of the wave motion is defined as the maximum displacement of a particle in the wave. Now here, when you're defining amplitude, with all these conditions comes the idea that maximum displacement. So when you're defining amplitude, some things are left out. For example, we are not talking about distance, we are not talking about specified direction when you're defining amplitude, and we are not talking about the equilibrium position. We simply say amplitude of a wave is defined as the maximum displacement of a particle in the wave. The reason why these conditions are omitted when you are defining amplitude is you are saying amplitude as maximum displacement. The amplitude is defined in terms of maximum displacement. Displacement is defined including these conditions. So when you are saying maximum displacement, these conditions come under that. That's why the definition in the book, this is the exact definition, exact words from the order publication book. They are omitting the idea of these equilibrium position and specified direction, distance move, because they are saying that it is the maximum displacement. But you don't know what kind of an examiner is going to show up when marking your paper, so it's better that you go, even when you are asked to define amplitude, you define in terms of distance, in which case you have to include all these conditions as well. So it's better to define amplitude as the maximum. Instead of saying displacement, say distance moved in a specified direction from the equilibrium position by a particle. So even when you're asked to define amplitude, please go to the very root, give it in terms of distance, and when you're giving in terms of distance, of course you have to include these conditions as well. Okay. Then calculate for the wave on the rope the amplitude. So calculating the amplitude, they are saying in that question here, in that 0.2 seconds, the point A moves a distance of 80 millimeter. The point A moves a distance of 80 millimeter during one oscillation. The point A moves a distance of 80 millimeter during one oscillation. Now during one oscillations means that the particle goes, let's say it goes down, up, then it goes to the top extreme and comes back, right? So this 4 movements is considered as 80 millimeters. So one part, which is the amplitude, will be equal to 80 divided by 4, that will be 20 millimeters. Okay, amplitude is equal to 80 divided by 4, 20 millimeters. Then they are asking you to find the speed. So speed, V is equal to F lambda. V is equal to F lambda. Now frequency, so I go to the question and try to see what other data are given. So the only other data, that is not the only other data, there are the 2 data given. One is 0.2 seconds, that is the time for one oscillation is 0.2 seconds, which means that period is equal to 0.2 seconds. And the wave on the rope has a wavelength of 1.5 meters. So the lambda is 1.5 meters. Now you know the lambda. If you can know the frequency, the period can be given. So the relationship between frequency and period is F is equal to 1 over T. So V is equal to 1 over t times lambda, that is equal to, so you can just do it, 1.5 over the period is 0.2, which will give you a speed value of 7.5 meters per second. This is 7.5 meters per second. Okay. Then on figure 5.1, draw the wave pattern on the rope at a time 0.05 seconds later than that shown. Now, so they are saying 0.05 seconds later. We know that the period is 0.20 seconds, right? So if the period is 0.20 seconds, then 0.05 seconds is after a quarter of a period. And if you consider the diagram here, the particle A is at its lowest extreme at the given time. So in a quarter of a time, it would go to the equilibrium position. It would reach the equilibrium position, right? So the particle A should be at the equilibrium position. And similarly, if you consider this particle, the wave is moving in this direction, the wave is moving towards the right, so this particle here should reach the situation of these particles in a quarter of in some time. So in a quarter of a time, this particle will be at the lowest extreme, like A now. So this particle will reach the position of A in a quarter of a time, and so on. The wave will kind of move or shift towards the right. So the pattern would be like, so if this is the dot line, okay, that is the equilibrium position. In a quarter of a time, A will be at the equilibrium position, then so this is A. So if you are comparing it with the earlier situation, earlier A was here, right? And so if you look at the corresponding point, this is A in the beginning, this is A now, and this is the blue one is the beginning, so it has come to this point, and then the top one in a quarter of the period will come here, and this one in a quarter of a period would go up. Of course, this amplitude and this amplitude should remain the same. There is a mistake in the drawing. And similarly, the lowest particle here, not like the side one, the lowest particle here should go to the equilibrium, and this one would come to the this position, the lowest position, and the one on top here will move to this point, and this one would go up, this one would go to the equilibrium position, and this one would come to the lowest, and this one back to the equilibrium position. Okay, so the idea is you have to imagine like the wave is moving to the right. It's like you are kind of literally dragging that blue line to the right. So you can see that if this particle is going to have the same experience as this particle in some time later, that means that after some time this particle should be at the same height as this particle. After the wave is moving to the right, that means this particle will have the experience of this particle after some time. So after some time, this particle is at its lowest extreme, so this particle comes to its lowest extreme. Okay. The last part, state and explain whether the waves on the rope are progressive or stationary. So there are many differences between progressive waves and stationary waves, but the key difference is in a progressive wave there is a net transfer of energy, but in a stationary wave there is no net transfer of energy. Okay, so this is a progressive wave because energy is transferred in net. You can see that the region here is kind of stable, but in a bit of time it is going to be hit by the wave and it's going to gain kinetic energy, this region. So obviously the kinetic energy from this region has moved to this region, so the energy is being transferred. So yeah, so it's a progressive wave. Longitudinal or transverse, it is transverse because the particles on the rope are, the movement of the particles on the rope is perpendicular to the direction of travel of the energy, propagation of energy. So the common mistake here is people tend to say that the wave vibrates perpendicularly to the direction of travel of the wave. It is not the wave which vibrates. Wave is a collective term. It is not one thing. It is the thing which vibrates is the particles. So in the definition again and again, I don't know how I can say it loud enough or often enough, but the common mistake is particles. That was a phrase from the WHO head, loud enough, often enough. Okay, so yeah, so that brings us to the end of discussion of the first structure.